All right, now we're going to try to figure out the center of mass for a continuous distribution of mass. The example I am going to use is this meter stick that you have already been thinking about in terms of finding the total mass for. And I'm going to use the chop, multiply, and add strategy that we use for constructing integrals in this course. The first stage, funnily enough, is fundamentally identical to the chop stage that you have already done. I've reproduced the picture here, which shows the full meter stick with a small piece of that meter stick, which I've labeled with a width dx, located at position x, and having a mass dm, which is equal to lambda dx. In this case, our meter stick has its mass uniformly distributed, so we can write the mass density as the total mass m divided by the total length L. For the multiply step, the thing you almost always want to do is zoom in on the part of the integrand that is inside of the integral symbol. So here that is r dm. So I'm multiplying together r, which is the position vector of the little piece, times dm, which is the infinitesimal mass that that piece has. In this case, if you've drawn a good picture up in your chop stage, you usually have all the important pieces. So here I have the x position as the location of this piece, which is just going to be x hat. And then dm is lambda times dx. And if I want to clean that up a little bit, I can write this as x, lambda x dx, and then I'll put the x hat over here for the direction. Last of all, I need to add up all of these little dx's, and I'll go ahead and draw a few more of them in here. And the way that you can do that for a continuous distribution is to do the actual integral here. So what I'm going to do is write down this RCM, which again, because I want a thing that has units of position, I need to divide by the total mass of the object. I need to do an integral, which in physics we almost always do definite integrals. Here that definite integral is over the meter stick, which is going to be from 0 to capital L. And then I need to put my RdM inside of the integral. So I'll put this piece in here. This is lambda x dx x hat, all of which is inside the integral. Some of these things are constant. The lambda and the x hat are both things that are not changing as I move from left to right along the meter stick. I can also plug in my expression for lambda here, which is m over L. That will cancel out the m over here. And so this is going to give me a 1 over L times the integral from 0 to L x dx. And then I'll put the x hat way over here to indicate that it's outside of the integral now. This is a relatively easy integral to do by hand. X goes to x squared over 2. Evaluated at the endpoints is going to give me L squared over 2. And then I divide by this factor of L, and I get L over 2. And then my x hat comes along for the ride here. And this now gives me the position of the center of mass for the meter stick, which hopefully doesn't come as too much of a surprise. My meter stick is uniformly dense and is 1 meter long. And so I'm going to expect the center of mass to be right in the middle of this object. Of course, you can quickly see how you could extend this model here to deal with an object that, say, had more mass down at this end than at this end by adjusting this, this density function as a as a function of x. And of course, we could also fiddle around with the direction if I wanted to think about not just the position in the x direction of this object, but the center of mass position in the x, y, or z directions.